Okay, as promised, we're now going to take a turn in our study of calculus and look at antiderivatives. Okay, so let's think about what they are. Suppose you have a function, f of x is equal to, let's take a kind of a common one, x cubed. Then we know that its derivative is what you get by bringing the 3 down, subtracting 1, and you get 3x squared. And we know there is only one derivative for any particular function. We have rules for doing it. An antiderivative, as the name implies, is kind of the opposite of this. In other words, what you're doing here is you're saying, what is the function, if there even exists a function, so that when I take the derivative of it, I get x cubed, okay? So that's what we're asking for. What is the function whose derivative is x cubed? Now, there isn't a good notation for antiderivative that makes sense until a little bit later. So I'm just going to use my own made-up notation just so that for right now we can talk about antiderivatives. So this thing right here, this stands for the derivative of function. Let's use this for the antiderivative. So the antiderivative of x cubed, let's see. How do I want to do this? The antiderivative, let's do it like this. If, no, we'll say, leave it like this. The derivative is 3x squared. The antiderivative of f is, what is the function? What's the function whose derivative is x cubed? So you have to kind of think backwards. Let's see. It's going to be something like x to the fourth because when you take the derivative of x to the fourth, you're going to get a 3 there. But we have to get the right constant in front here. And I think what will work will be if you put a 1/4 there. 1/4 x to the fourth. Because if you bring the 4 down, that cancels with the 1/4 and you get x cubed. So there's the derivative. There's the antiderivative. Okay, so let's do a few more as long as we're just learning about this. Notice I haven't given you any reason at all why you'd even want this. And by the way, let's also be clear that whereas there was only one antiderivative, or there was only one derivative here, there's all sorts of antiderivatives. Here's one, here's one, here's another one, okay? But what we did learn back when we studied the mean value theorem is that any two that if two functions, here's what we learned. That if the derivative of f is 0, that implies that f is the constant function. So because of that, if the derivative of f of x minus g of x is equal to 0, that implies that this function is the constant function, which means that f of x is equal to g of x plus the constant. Okay, so what we proved is that if you have any two antiderivatives of a function, the only way they can differ is just by a constant. You can't have any other fancy thing when you take the antiderivative, you end up with something totally different. So once you find one, you've basically found them all. All you have to do is throw in the constant. So to get them all, we just kind of put a C there to indicate there's all of them. Okay, so let's do another one. Say the function is the sine of x. Then we know that the derivative, just to review, is the cosine of x. What's the antiderivative of f? What's the antiderivative? What's the function whose derivative gives me sine? Well, it's kind of the cosine again, isn't it? Because the derivative of the cosine is, it's the negative of the sine. So if I put a negative right there, I think I should be safe. The derivative of this thing is the sine of x. Okay, let's try another one. How about, we'll call this one g. If g of x is equal to e to the x, then we know that the derivative is equal to e to the x, and the antiderivative is also going to be e to the x. That's about as easy and plain as it gets. Let's try one a little bit harder. How about h of x is equal to e to the 5x? Then the derivative is going to be 5e to the 5x, and the antiderivative is, let's see, how are we going to do that in reverse? Since the derivative ends up putting a 5 down front, I think it will work to put a 1/5 there. Let's check it out. You can always just guess and try. So if you take the derivative of this thing, what are you going to get? The 1/5 stays right there. The derivative of e to the 5x is going to be e to the 5x times 5. That 5 comes and cancels with this, and sure enough, you end up right there. Okay? What about some other ones? What about if f of x is equal to 1 over x squared plus 1? We won't bother with the derivative. You know how to do that using the quotient rule or the chain rule. But I'm more interested in, do you remember what the antiderivative is? What's a function whose derivative is that? Do you happen to remember it? It's the arctan of x. The derivative of this thing is that right there. Okay? Do you know what's the next one's coming up? If I have 1 over square root of 1 minus x squared, what is the antiderivative of that? Do you remember? It's the arc sine of x. And again, I should have plus c's on all these things, okay? Plus c's all the way through. Okay? So there they are. So I think, let's see, that's kind of it. Those are some of the antiderivatives. Then, you know, you could get a little fancier. You could say, what about if the function is 5 times the square root of x plus 1 over x cubed plus 1 over x? Well, let's see. Let's rewrite that. That's going to be 5 times x to the 1/2 power plus x to the -3 power plus x to the -1 power. Agreed? So if we take the antiderivative, here's the antiderivative. You can just break them up into pieces for the same reason that when you take the derivative, you just break them up into pieces. You can do the same thing here. So what's the antiderivative of this? You would add 1, so it'd be x to the 3/2 divided by 3/2 is the same as 2/3. So if I multiply 5 by 2/3, I'm going to get this. Check it out. If I multiply this down, I'm going to get 3 over 3 cancels, and I'm going to get 10 over 2, which is 5. And then I subtract 1 there. That looks good. What about here? If I add 1, it's going to be x to the -2 power divided by -2. So you can write it like that if you want. And then what about here? X to the -1. So if I add 1, x to the 0 divided by 0. Whoa, something's wrong there. It worked for everything else. Why doesn't it work here? This is no good. No good at all. Do you see what is the right answer? Do you remember? What's the antiderivative of 1 over x? What's the function whose derivative is 1 over x? Ah, it's the ln of x. Aha, indeed. It's the ln of x. Actually, the best answer is the ln of the absolute value of x, because it turns out that for either positive or negative values of x, this is a function with a larger domain, and the derivative of this thing is equal to this. So plus c on the end. Okay, so there's antiderivatives. Okay, so that's how to do them mechanically. Now the question is, why are we interested in them? Well, one reason we're interested is because recall that they are related to motion problems. We've had problems before where we started with the position of an object, and then once we had that, we took the derivative, and that gave us the velocity, and once we had the velocity, we took its derivative, and we got the acceleration. Quite often, things really you want to go backwards. In fact, kind of historically, that's what happened. We learned from experimentation for falling bodies that there's a uniform acceleration for falling bodies if there's no if there's no influence of air resistance. Okay, so so falling bodies, you have this acceleration due to gravity if you're close to the Earth's surface, which we typically just designate as negative g in units of feet in seconds. G would be negative 32 feet per second squared, or negative 9.8 meters per second squared. But anyway, it's g, and so that's your acceleration. And so if you take the antiderivative of the acceleration, you get the velocity. So what's the antiderivative of a constant? It's just going to be that constant times the variable t plus some c, okay? So I could call that c, but I'm going to change it to something which is a little more suggestive. Notice if this right here is the equation for velocity, then the velocity at time 0 is going to be 0 times this, which is 0, plus c. So that tells me that c is actually the initial velocity. And quite often you put a little v sub 0 there to indicate the initial velocity. So so that's the initial velocity before you subject it to gravity and so on like that. So I'm going to write it like that instead. It's still just a constant, but it tells you that that's your initial velocity. Then once you have that, how do you find the height of the object? And again, that's going to be the antiderivative of this. So we're going to have to add 1 and divide by it. So it's going to be negative g over 2t squared plus v naught times t plus another constant c, which for the same reason as before, I'm going to call that h naught. So anyway, there's formulas for falling objects, and you start with the acceleration and you work backwards to get the position, or in this case the height. Okay, let's look at another example. We already did a bunch of them along those lines. Here's one I kind of like. Let's say that Elvin leaves Holland, Michigan, that's where I live, at noon. We'll say t equals 0, traveling north with velocity v of t is equal to 20t plus 40 miles per hour. And this is Elvin's velocity, so I'm going to put a little v sub a there to stand for Elvin. Okay. Beth leaves Muskegon, which is 30 miles north of Holland, at the same time, at t equals 0, with velocity v sub b equals 60 miles an hour. So notice that Beth just travels at a constant speed, velocity, straight north, and Elvin, he's playing catch-up. First of all, she's starting north of him. He's starting here. They're both heading north. So she's starting 30 miles north, and she's also starting off faster. But notice that he's speeding up, whereas she's not. So intuitively, you'd probably guess pretty easily that at some point he's going to catch up with her. And so let's ask, when and how far from Holland will Elvin pass Beth? And that's why I like to use A's and B's. Will Elvin pass Beth? Okay? So, kind of a nice problem. Let's see what we can do. So let's first of all find Elvin's position. So the position for Elvin, I'll use P P sub A for Alvin's position is going to be the antiderivative of this. The antiderivative is going to be 10t squared plus 40t plus c, and c will be the initial position, and we'll assume that Holland is, everything is fixed here at Holland, so the initial position will be in relationship to Holland, and since he's starting from Holland at time equal to 0, we want him to have position of 0. So at time equal to 0, this is going to be 0 plus c has got to be 0, so that c's got to be 0. So we have that. The position for Beth is the antiderivative of this thing, which is going to be 60t plus c. And notice that Beth is 30 miles north, so at time equal to 0, we want her position to be 30. So that's going to be like so. So now, when will he pass her? In other words, when will Alvin's distance be exactly the same as Beth's? So you see that that's a little algebra coming up here. So we'll write 10t squared plus 40t is equal to 60t plus 30. Let's first of all just divide everything through by 10. So we're going to get t squared plus 4t equals 6t plus 3. Bring everything over to the left-hand side. T squared minus 2t minus 3 is equal to 0. Factors nicely as was designed. T minus 3, t plus 1 is equal to 0. T is either equal to 3 or to negative 1. Negative 1 doesn't make any sense physically. If we could go backwards in time, that would be another point where they had the same distance. But going only forward in time, there's when he's going to pass her. And now to find out where the position is, you should be able to put that into either of these. Either one will work. This one looks like it might be a little bit easier. P sub B for 3 is equal to what? 180. 60 times 3 plus 30 is equal to 210. And we might as well check it out. If you put a 3 in here, you're going to get 9. 9 times 10 is 90 plus 120. 90 plus 120 is also 210. So there's how far he is from Holland when he passes her. Okay, so there's a place for antiderivatives. But before we give up on this one, I want you to see something else, which is rather important, okay? And I'm going to be kind of teasing you over these next couple of lessons, not giving you the full answer, and that will come in about 2 or 3 lessons from now where everything gets tied together. So right now, I want you to be asking and thinking of the right questions. I have something called, my last name is Penning's pedagogy theory. And the idea is that before you can learn something effectively, if you just are taught something without ever thinking about it, it's like all that information just sliding off the top of your brain. But if you ponder it, if you start wrestling with it a little bit, you form a little divot in your brain, and when you're given the answers, you get this kind of a aha feeling as it sinks in, okay? It becomes part of you. You own it, okay? You own it. And so what I want to do here is to kind of get you pondering about some things before you get the final answer. So anyway, here's what I want you to notice. If we just happened to graph, let's do Beth first. If we graphed Beth's velocity as a function of time, notice it would be pretty boring. Okay, in fact, I'm going to put them both on the same graph. I think that's going to be advantageous. So this one right here is v sub b. Her speed, so this is just velocity right here. Her speed at any time just stays 60. At any time it's 60. So if you wanted to know how far she'd gone after an hour, she'd gone 60 miles. Now notice, here's 1 hour, here's 2 hours, here's 3 hours, here's 4 hours, and so on. If you wanted to know how far she'd gone after 2 hours, that's going to be 120. I just want you to notice something. Notice that the first answer of 60 is exactly the same as the area underneath this graph. the answer to 2 hours is 120, which is the area, again, under the graph from 0 to 2. Same, no matter how far. 3 hours, she's gone, this is how far she's traveled now. It's not her position, but it's how far she's traveled. The amount that she's traveled would be 180 miles and so on. Okay, that's how far she's traveled. On the other hand, that was Beth. On the other hand, if we graph Alvin's velocity, it starts down here and it increases like this. Okay, now again, I got to be careful here. I'm mixing two things up just a little bit. I'm talking about how far they traveled, not their position. Notice she had a 30-mile head start. So so now I'm just interested in how far they're traveling. It's that right there. It's how far they've traveled in 3 hours. Okay. So so notice for Alvin, if we think about him, how would we figure out how far he traveled after a half hour or after an hour or so on? How would you get that? Here it was easy. It's constant. One thing you could think of doing here is if you had someone else in the car with Alvin, every 5 minutes they could ask Alvin what his speed was. And every 5 minutes he'd give them the speed, and then they would calculate if you had gone exactly that speed for 5 minutes, how far would you have traveled? So notice it's the same thing as here. We're assuming that it's constant for that 5 minutes. The next 5 minutes, you call again and you say, hey, what's your speed? Alvin, or whoever is looking at the speedometer, gives the speed, and you again calculate that for 5 minutes or 10 minutes or whatever this is. You do that every few minutes, and every time you do it, you're effectively forming a whole bunch of little rectangles. See that? Every time you ask the speed and you use that speed to say, well, if we go at that speed for this next 10 minutes, how far will we have traveled? You're effectively finding the area underneath that. After another 10 minutes, you ask the speed again and you say, oh, if we were to continue at that, how far would we have traveled? You're that. So notice that what we're effectively doing is getting an approximation for the area underneath this thing. See that? We're getting an approximation for it. And you can also see that you're going to get a better and better approximation if instead of doing it every 10 minutes, if you do it every 5 minutes or every 1 minute. And you can kind of see that this thing here that we're kind of gaining towards is kind of the idea of a limit again, where we're saying, hey, we're going to end up with the area. We're going to end up with the area underneath this graph by taking the limit of these little rectangles as you get more and more narrow. Okay, and not only that, but it turns out that the area underneath this graph looks like then that it compares to the distance that Alvin's gone. So the distance that Alvin has gone is both you get by looking at the antiderivative, and you also get it by looking at the area underneath the graph. See that? We got it here by doing the antiderivative. Here we're kind of getting it by looking at the area underneath the graph, and that suggests that maybe, just maybe, there's some connection, some important connection between the antiderivative of a function and the area underneath the graph of the function. In fact, that's exactly what the fundamental theorem of calculus is all about, so that will be coming up within the next couple of lessons. Lots of good stuff.